All right, Calc folks, back here with the last lecture video here in my series of lectures on the application of integration, where we are in a bit of lecture here where we're looking at how to use the integration process to perform some calculations we might encounter in a physics class, right? Some physical application. If we take a look at, or keep in mind what we've looked at so far, is we have considered the case for mass with variable density and the case for work done by a variable force. What we're now going to do is look at the situation done, the situation for the case of work done by lifting fluid objects, folks. And that's what we see happening here in this set of notes, right? We are going to look at work done lifting fluid objects. And lifting fluid objects is a little different than what we think of as being lifting solid objects. And we're going to distinguish between the two, right? Lifting a solid object against gravity, right? Against the force of gravity. The work done lifting the object is going to be described by force times distance, right? The force that we have to apply to lift the object times the distance at which we lift this solid object is going to give us the work we have done to lift this solid object. All right. Where if we go a little further, when we're lifting objects against gravity, well, first of all, when it comes to force is always just mass times acceleration, right? If we know the mass of the object and we know the acceleration of the object, right? That mass times the object's acceleration is going to produce a force, all right? We can measure then the force of that object. The force, right, for that mass moving at a certain acceleration. All right. So in R3, right, if G is the gravitational constant, rho describes density, and V describes the volume of the object, force is really just going to be given by density times volume times the gravitational constant. Whereas in R2, force is rho times area, density times the gravitational constant. And when in the case of one-dimensional space, force is the density times length times our gravitational constant, where we were introduced to this idea of density occurring in these different regions of space and having thus different setups for what would be maybe thought of as our mass calculations relative to those descriptions of space. All right. This is going to be the force calculations that we're going to work with when lifting objects, lifting either an object in one-dimensional space, lifting an object in two-dimensional space, or the case for the force necessary to lift an object in 3 dimensions. All right. I do work through an example of this. For example, consider lifting against gravity a sheet of plywood with a density of 12 kilograms per meter squared up one flight of steps, right, over a distance of, and I erased the distance there, a distance of 1.8 meters. No, wait. Over a distance of, erase the meters. Can I get it back? No, probably not. What was it? 12. This is the force. Oh, 4. It is 4. It is 4. We see it down here. Distance of 4 meters. I thought it was 4 when I wrote the problem, right? Assuming we are lifting the object against gravity on Earth, right? If the sheet of plywood measures 1.8 meters squared, the force necessary to lift this object is described as we see here. It is the density of the object times the actual area description of our object times the measurement for the acceleration due to gravity, giving us a measurement of force that is 211.68 kilogram meters per second squared. All right. And when lifting this plywood over a distance of 4 meters, well, it's just going to be this result, right, times that distance of 4, which gives us 846.72 kilogram meters per meter per second squared, right? Or what is essentially 846.75. Let's go 72. I don't know where that 75 came from. Newton meters. A Newton meter is 1 kilogram meter per second squared, right? Here we're looking at 1 kilogram meter per second squared. So one of those meters is held out in our description of work and our labeling. Right? Now that is lifting a constant object in the work calculation for lifting that constant object. Now when lifting a fluid object against gravity, the entire object is not being lifted all at once. Right? For example, consider lifting a coil of rope off the ground, just holding on to one end of the rope. Right? Holding on to just one end of the rope and lifting upward. Right? If you had a coil of rope on the ground and you just grabbed one end of the rope and started to lift it upward, right? As you lifted, more and more of the rope in the coil is going to end up being lifted. Right? Indicating more and more of the mass is being lifted. Right? And indicating more and more work is being needed in our calculation here, folks. Right? Furthermore, at the moment in time when the entire rope has been lifted off the ground, it turns into a case for lifting a solid object, since the object's mass will no longer be changing as we lift that object. As soon as all the rope is lifted off the ground in this manner, it will become the case of lifting a solid. All right. For example, in one-dimensional space, consider lifting a 5-meter rope with a density of rho equal to 0.1 kilograms per meter against gravity in the manner described above, having it coiled up and picking up just one end and lifting it up slowly out of the coil, letting it uncoil as you lift. All right. Overall, the rope has a mass of 0.1 times 5 meters, or 0.5 kilograms. If we were to lift the entire coil of rope, right, all at once over a distance of 10 meters, let's say it was all tied up into a bundle, or it was in a box and we were lifting it up in the box, right? We would have to factor in the box, but the work done just lifting that solid coil of rope, right, a distance of 10 meters, would be 0.5 kilograms times 9.8 meters per second squared times 10 meters. It would be this mass times the acceleration times the distance that we lifted it, which in the end would correspond to 49 Newton meters. Whereas if the rope is lifted, right, by holding on to one end of the rope and lifting it as it uncoils along the way, the mass of the object is variable. Since the length of the rope is variable at any point in this initial lifting motion, right? Consider the following approach for calculating the work done here, folks. And this is what we're going to find with any generic lifting fluid object problem, folks. We are going to have to set them up generically speaking, right? They are going to have to be set up for each and every situation. We're going to see at the end there is one special case that we can consider, right? But we're going to run into these really in generic context, being very much a different setup that follows a similar process each and every time. All right. All right, folks. What we see in this calculation, right, if we consider lifting it by uncoiling it, just grabbing onto one end and lifting, right? The way we approach this problem is we begin by arranging the rope vertically in our one-dimensional space, right? We would imagine it in our one-dimensional space starting here at the ground level and being lifted up to that point at which it becomes a solid, right? We would consider the vertical extent over which it would maybe be thought of as a fluid object as it gets uncoiled, lifting at that distance of the first 5 meters in our lift. the rope will have to behave as a solid at this point, right? Whereas distance of y in this lift, less than 5 meters, the rope will actually behave as a fluid, right? So we're going to consider just arranging the vertical rope as if it was moving through the first 5 units, right? For the portion from 0 to 5 where it might be thought of as being fluid, right? At this point, we're now going to subdivide the rope into n sublengths vertically, right? We're going to go through and cut up that rope vertically over that interval from 0 to 5 where it's behaving like a fluid, right? And cut it up into n sublengths. And we're going to let delta y be the width of each of those sublengths. And we're going to let y sub k be an observation of y in each of those k sublengths. And from our understanding of the work needed to lift a solid object, right, in one-dimensional space, work would be equal to rho times g times the length times the distance over which we lift. Rho being density, g being our gravitational constant, L being length, and little d being distance. So if we wanted to approximate the length to lift just one of those little subintervals of the rope, right, it would be rho times g times delta y, the length of that little subinterval of rope, times y sub k, right? Y sub k is going to describe the distance that that little subinterval of rope had to be lifted, right, from the ground level up to its current location, right? We're in this case, rho and g are certainly constants, right? Implying an approximate of the total work needed to lift the rope then could be given by this summation seen here, where rho and g being constants can be factored outside of that summation, and we can work with what we see here on the right hand side, right? Where to make that summation exact, to make that calculation of work exact, we apply a limit as n heads to infinity, and a limit applied to this with the rho and g being constants. Rho and g will be factored outside of the limit calculation as constant multiples, and you'll be just left with the limit of this Riemann summation. Let me scroll down and get that into view, where from the definition of the definite integral, right, the limit of this summation can be rewritten as this calculation seen here on the right hand side, this integration calculation. We really are just going to integrate over what would be called y, the description of the distance at which each sublength has to be lifted with respect to y for every single sublength from A to B here, or from what we should say maybe is 0 to 5. Right? Because that is our interval over which we are integrating here, folks, in this specific case. So in our case, the work needed to lift the 5 meters of rope off the ground, a distance of 5 meters, right? The distance over which it's going to behave like a fluid, right, would be given by the following integration calculation here. Rho would be 0.1. G would be 9.8. We'd integrate y from 0 to 5, so that will become 1/2 y squared. We're evaluated from, well, first of all, 0.1 times 9.8 is 0.98, which is 98 hundredths. The antiderivative of y is y squared divided by 2. So you can bring that 1/2 out and cancel with the 98 and build 49 100ths, where y squared evaluated from 0 to 5 is 25. The 25 will cancel with the 100, leaving you 4. So the total work done here, let me scroll this up so you can see this. The total work done in this calculation, right, is 49 force Newton meters. All right, is this measurement of 49 force Newton meters seen up here. All right. Now, if we lifted another additional 10 meters up to a height of 10 meters, we're going to lift it 5 more meters where it behaves as a solid. All right. So lifting it 5 more meters where it behaves as a solid, I see that I have an error in here. And maybe we can... This was considering the case of lifting at 10 as a solid. So the case for lifting at 5 as a solid would be half this measurement. So instead of 49, I should actually have 49 halves. All right, because we're just lifting it another 5 feet as a solid, or 5 meters as a solid. So that is going to change this result here. So what is that going to be? That's going to be 98 force plus 49 force is 147 force, if I'm not mistaken. All right, so that would be 147 force Newton meters. All right. All right, so I just went over and checked that. That is absolutely correct. 147 force Newton meters. All right. Now, this previous example illustrates the variable nature of lifting fluid objects. All right, and the approach of calculating the work by developing this integral calculation specific to each case, a lifting in our n-dimensional space, n being 1, 2, or 3 dimensions. All right. The case of lifting of fluid objects varies greatly from case to case, right? Sometimes we're lifting objects off the ground. Sometimes we're curling them over the top edge of a building, right? Or you know, they're dangling, and we're lifting them hoisting them to a certain height, right? So their cases can vary, and they're not always one-dimensional cases of a rope. Sometimes we're lifting 2-dimensional cases of maybe a flag that's dangling, or a screen, right? Maybe we have a projector screen that lowers down and then has to be raised back up, and as it raises up, it curls up, and as it curls up and gets raised higher and higher, the amount of screen that's dangling, it gets less and less, and the amount of mass that's dangling gets less and less. So the work necessary would be variable there, folks. It would behave a lot like a fluid object. All right. There is one specific case, though, that we do consider here, where we are given a formulation in the book, and that is the case of pumping a fluid from a vessel to a given height in 3-dimensional space. All right. There is a calculation for this, and it is given as follows. All right. This is work done pumping fluids. All right. Assume the vertical extent of a fluid, all right, with density rho in some vessel can be described by the values of y in some closed interval from C to D. All right. So let's say we had this vessel, and there was this vertical extent of fluid in that vessel. Maybe it's from just the floor of the vessel to halfway up it, or maybe it's from the floor of the vessel to 3/4 of the way up it, or maybe it's from the floor of the vessel to the top, right? The vertical extent of that fluid is going to be described by the variable y, right, up and down in 2-dimensional space. I realize we're working in 3, but the problem is going to set itself up this way, where y is going to be this vertical extent that's going to go from C to D, not to the top of the tank always, only if specified, but C to D is only the vertical extent of the fluid. All right, letting A of y describe the areas of the horizontal cross sections of the fluid. You're going to take the fluid filling up this vessel, and you're going to slice it up horizontally into cross sections, and you're going to be able, if you can, hopefully at each of those cross sections, at each of those layers of y, you have a way of finding their area. We're going to let A of y describe that area, And we're going to let DOI describe how far each of those cross sections need to be lifted to be considered to be pumped out of the vessel. All right? If AOI describes the area of the horizontal cross sections and DOI describes the distance that each cross section must be lifted, then the work done pumping or lifting the water against a gravitational constant, right? Lifting the fluid. I should really be careful there. Against a gravitational constant G is described by what we see here. All right? It is rho times G times the integral from C to D, that interval over which the vertical extent of the fluid exists, with an integrand given by just simply our area of Y, AOI times DOI. AOI describing the area of our cross sections, DOI describing the distance that each of them must be lifted. All right, let's look at an example. For example, right, suppose a conical tank is filled with the fluid, or with a fluid, that must be pumped over the top edge or lip of the tank. All right. If the conical tank is in the shape of an inverted right cone, that means its tip is pointing down, right? With a radius of 4 meters at the top, right? It has a circular radius at the top of 4 meters, and a depth of 8 meters. That means from the top all the way down to its tip is 8 meters in depth. What's going to be the work necessary to pump out that tank if filled with a fluid? Well, in the case of the vertical extent of the fluid, it can be described over values of y in the closed interval from 0 to 8. Right? As for the shape of the fluid's horizontal cross sections, if we take a cone and we divide it up horizontally when it's orientated tip down, right? All of its cross sections are going to be circular in shape. Right? Where we know how to find the area of a circle, it's pi r squared. Right? And these circles are all going to have a radius somewhere between 0 and 4. If the top of the tank has a radius of 4, right, the very tip of the tank is going to have a radius of 0. And as the cone forms from tip to top, it's going to grow in radius from 0 to 4. Right? And pending the value of y where these cross sections held, there will be a different radius, all dependent upon the value of y. And we can note the following little illustration here. Right? Here is the profile of our conical tank of fluid. Right? And we can see that if we were to slice this horizontally and revolve that slice around the y-axis, it would form a disc or a circle in shape, where that circle we know is going to have an area described by pi r squared, and its radius is going to be the distance here. The distance from the y-axis out to its edge, where this distance is really just an x value. Right? And that x value can be used by noting the relationship for the edge of this conical tank in this orientation. If it has a radius of 0 at the tip and a radius of 4 at the top, then the edge of the tank, if orientated with its tip at the origin in our system, can be described by the line x equals y divided by 2, or x equals 1/2 y. So if I'm at a height of, for instance, 5, or at a depth of 5 along my y-axis, the actual radius I would see there would be 5/2. We can go over here and see that is the actual depth of our tank. Here's 3, here's 2.5, or 5/2. That would be the radius that happens at this depth marker of 5. At 6, it would be 3. At 4, it would be 2. At 2, it would be 1. All based upon this relationship. So y over 2 is going to end up describing our radius. So in the case of our the area of our circle, right, from the formula where pi times radius squared, it's going to be pi times the quantity y over 2 squared, which simplifies to pi over 4 times y squared. As for the distance you got to move each cross section, for instance, this distance, this cross section here for this radius, it's going to have to be lifted 3 units. All right? To calculate that distance for each and every value of y, dy is simply 8 minus y. Right? At y equal to 5, it would be 8 minus 5, or 3 meters, is how far we have to lift that cross section. Right? So, in the case of this tank, assuming it exists on Earth, the work done pumping the fluid from the tank would be given by 9.8 rho, 9.8 times the density, times the integral from 0 to 8, for the quantity a sub y times d sub y, where a sub y is pi over 4 times y squared, and d sub y is this quantity 8 minus y. The pi over 4 is a constant multiple. It can be brought out with the 98 tenths and made into 98 40ths of pi times our density, where our integrand, if we expand the y squared with the 8 minus y, becomes 8y squared minus y cubed, whose antiderivative is 8/3 y cubed minus 1/4 y to the 4th, where when evaluated across the bounds from 0 to 8 yields 1,024 thirds. Multiply that by 98 pi over 40, and you do get that to simplify to 12,544 15ths of pi times rho, our density, Newton meters of work. All right. Now this calculation does keep rho at the moment variable, not really defining what type of fluid we have here. But if it is the case that we are dealing with water, in the case of water, rho would be equal to 1 kilogram per meter cubed, and work would simply be the numeric value we were given here, this constant multiple, 12,544 pi divided by 15 Newton meters, or which is about 2,672.21 Newton meters of work. All right, folks, this is lifting fluid objects. This is the specific case of pumping a fluid from a tank. To approach that problem, you're going to subdivide your vertical extent of the fluid from C to D into n subintervals. Right? You're going to figure out how you calculate the area of the cross section for each of those subintervals, and you're going to figure out how far they have to be lifted to the top of the tank, or to the height where they're considered to be pumped from the tank. All right? With the area description and the distance description in terms of y, they can form your integrand from that product, where you then integrate over that vertical extent of the fluid. Multiply that by the density and the gravitational constant, and you have your calculation for work. All right. Folks, again, this is the last of our looks at application of integration here. Some of what we want to take away is the integration process, but also the formulations presented in this section. And more so than the formulations is that integration process. That is kind of the implicit understanding that we need to be developing from this section, right? This chapter of material. But this does finish with what I want to discuss this semester in terms of applying integration, or at least putting videos together. We are going to be in class maybe seeing a couple other ideas develop here, but we'll see about all that. We do have to start moving forward in our lectures. What we're going to move into next here is looking at some integration technique. But before we get to the integration technique, we got a small little bit where we introduce ourselves to exponential models, right? Exponential and log modeling. And we're going to look at the hyperbolic functions and their calculus results, right? We're going to add those to the mix here, folks. We're not going to spend a lot of time there. We'll be into the techniques for integration pretty darn quickly and be moving on from there. So with that said, I'll end this video. It's right at about a half hour. Again, I'm trying to keep these quick so that they're not so overwhelming, and this does finish the last in this series. So I hope you're all doing well. I'll see you in class very soon.